Alright, hell yeah. So this is guesstimation. We're doing engineering statics. This is book of Hibbler. And we're going to do this probably 3 or 4 ways. We're going to try to do it as fast as possible. So how would you guess, how would I guess the answer? So I'm going to use a few techniques. Well, actually, I'm going to start with the most rough because it's kind of cool. It applies this principle that approximately 60 degrees is 1 radian. And what we know about, let's say, just a half a radian, so 30 degrees, let's say this is half a radian, that if this is a distance of 1 meter, this is a distance of 0.5 meters. So this value right here, the angle in radians, is equivalent to or like the fraction of the whole. If this is a half a radian, then this distance is going to be half the hypotenuse. You know what I mean? And so that's what we're going to be using. So this idea, then we can do 40-degree triangles. Because this has a 40 degree. You should just memorize 60 and 30. But actually, because our first estimate is that a 60-degree triangle, like let's say I have a 60 degree. What I'm estimating there is if this is 1 meter, I'm saying that this component is 1 meter as well. It's 0.866 meters, but that's going to be the first estimation. And that's really rough, but we can still use that same linearity up to 60 degrees as we do for a 40-degree triangle. So if I'm saying 60 degrees is 1 radian, 30 degrees is a half a radian, well, hell yeah. So what is 40 degrees? Well, if this is 1 radian, I'm going to do 60 divided by 40. So that's going to be 2/3 a radian. So I can just kind of see that 40 degrees is 2/3 a radian. And yeah, one of the commenters is just like, yeah, what do you do with a 40-degree triangle? And then, yeah, so here I'm estimating it. And cool. I guess I'm kind of bummed out because the 40 degrees isn't actually, I misread this problem. We need to find the components in the x direction and kind of the y direction. This is going to be the positive. So we use the fact that if, let's do this one. So we have the two components. Like I said, this is a 60-degree angle because this is 30 degrees. I'm just saying this component is 200. This is going to be half. Now I can know that just from sine of 30 is half. I think everyone knows that. No one's going to forget that. But it's just kind of useful from this rough estimation. Where is my linear approximation? I'm taking the small angle theorem all the way up to 1 radian just because it actually defines, it's cool because it defines what a radian is. Like it says, hey, if this is an angle of 1 radian and this is 1 meter, then this vertical distance based on that approximation is approximately 1 meter. Cool. And that means that 30 degrees, based on that linear approximation, is 0.5. It's going to be 100. It's going to be half this. It just happens to be that sine 30 it is exactly half of the hypotenuse. But, we're just kind of doing that initial rough guess. So I guess right here I got 2 options. I could treat this as a 70 or I could treat this as a 20. And hell yeah. So now we can come back to here. 40 over 60 was 2/3, but 20 over 60 is a third. So now that I know that I have a third, so whatever this magnitude is, I know that in the sine direction, this direction, I'm going to have a third of it. So I'm going to have 500 divided by 3. I don't know what 500 divided by 3 is. Alright, let's try something else. What's 1500 divided by 3? That's going to be 500. Oh yeah, we're back in the same boat. We got to divide 5. I can't divide 500 by 3, but guess what? I can divide 300 by 3. That's 100. And now I got 200 extra. I don't know what 200 divided by 3 is, but I do know what 100 divided by 3 is. That's going to be 33, and then it's just like, oh yeah, no duh. So this is going to be 166. And sweet. So we're going to have a component of 166 there. I think if I really wanted to have a very rough guess, because that was too much for the first time. I would just approximate this to be 15 degrees. You know what I mean? Take percentages that I know. If sine 30 is half of this, sine 15 is a quarter of this. And so a quarter of this is just 100 and 125. So that I'm going to put this as my first guess. So I have 125 right there. We have a very small angle. That means this is 70. Any angle that's, if this is 30 degrees or less, and this is 60 degrees or more, like I said, I'm just saying this is 500. So now we can find our resultant. Our resultant is going to be, and we're going to use this one now. We're going to be in the x direction, 325, so we have 325 I, and then in the j direction, we're going to have 600, minus 600 j. So those are our two components, and hell yeah, now I get to use Pythagorean's theorem approximation. So I'm going to say if this is 1 and 1, this is going to be 1.4, but my initial guess is going to be 1 and 1 and 1.5, which is, if I turn this to 100, this is 150%. So there you go. So as percentages, which is actually the same thing as, anyway, yeah, so 100, so whatever the larger value is, if these are the same, it's 150%. But what do we have? We have a component, this is half of 600 is 300, so we have a component that's about half. What I know from my estimation is that if this component is half, then it's only 110%. And so I do have a little chart on this if you want to kind of pause the video. So here's Pythagorean's theorem, and I'll make a better chart that's more legible. But here's for a right triangle. Here's in 3 dimensions. You have 3 sides, A, B, C, and the hypotenuse is D. This is side A and B, and hypotenuse is C. So I can see that if both sides are the same magnitude, and what I'm looking for is I'm trying to find the triangle, the side with the larger magnitude, and then compare the other side. Is the other side half of that larger magnitude? Because if I have something like 7 and 3.5, well, hell yeah, then I know that this component is going to be half. Then I know that if this is half, then it's then the hypotenuse is 110%. So there's only a couple values here that are needed. Like one is like 150% or 140%, however you're going to approximate if they're both equal, 45-degree triangle. If one is 75%, I'm trying to remember that is 125%. And I don't think of it as 100. I think it's easier just to think of these numbers as, the addition. I'm taking the larger number and then adding 40% if both of those are the same. That's how I get that 1.4 ratio. So if this is 75%, taking the larger number and adding 25%. So in this case, that would be 12. It will be 12.5. I rounded all these numbers. Sorry about. I should have rounded. Anyway, and then if this is half, then hell yeah, I got 110%. If this number is less than half, it's who cares, especially for that first initial guess. All right. But we have just a little bit more than half, so we do care. So we're going to take our magnitude, which is our large. We're going to take the largest number and then add 10%. 10% of 600 is a $60 tip. Dang. And then so we have a magnitude of 660. So this is my magnitude for the problem. 2 forces act on the hook, determine the magnitude of the resultant force. All right, now let's look in the back of the book and see what. Let's try to get more accurate. Let me print this one off again. Alright, hell yeah. So I shoveled some snow, so it's been a little while since I took a break from this problem. But I'm just going to go over, if I didn't write anything, I'm going to say, hell yeah, this is 200, this is 100, this is basically 500 because the angle's even smaller. This is 20, I'm just going to make it 15 because then I'm going to do a quarter. This is 125. So there we go. And we're going to be 325 that way. And then 600 down. So, hell yeah. So we got that 325, 600. And then in my head, the 600 is the bigger number. The other number is half. So when we come to the, we got a triangle basically like this. And I mean, at the end of the day, if we're approximating 60 degrees, like this 60 and this 30, if we're saying that this longer component is going to be the same as the component, like we really should, for our first guess, just say 600. You know what I mean? I think it's a second guess to say, oh, if this is half, then it's going to be 10%, and we're going to do that. And then just going back to my chart, the only ones that I care about when it comes to a right triangle are if both sides are the same, then hell yeah, it's going to be like a 1.5. You know what I mean? Second guess will be a 1.4, get more accurate. And then if it's just half, I think 40% and 10%, those are my go-to. If I can remember the one in the middle, you know what I mean, at 75% when they're fairly close, you know, it's going to be a 25% increase. All right, sweet. So now we can go on and try to guess a little bit better. So I know that the cosine of 30, and I guess I just know this from a fact, that the cosine of 30 is 0.866. There's only a few that I actually know. You know, sine of 30.5, sine of 45.707. But even for this guesstimate, if we have anything with 45, I'm just going to say it's 0.7. And then let's see what we have. So this is going to be 0.86. I'm just going to round to 0.9. So that's what we're doing this round. I don't know what 0.9 of 200 is, but I do know what the 10% tip of a $200 dinner is. You know, I mean, holy hell, we got to pay 20 bucks. So 20 times 9, maybe I still don't know what 20 times 9. I know what 10 times 9 is. It's not, that's 90, you know. But anyway, instead of 20 times 9, do 2 times 9. Cool, that's 18. So it's going to be 180. Sweet, so we got that. People say stay away from the calculator, but that's kind of, that's my rust. No, I don't think so. I think it's just human nature to feel like inferior when just doing simple arithmetic. But you shouldn't, because it's difficult. It's some of the hardest thing to do, simple arithmetic. All right, so moving on, what are we going to do for this one? Well, the angle is going to be 70 degrees. This is going to be 30. You know what I mean? I mean, I should at least approximate it to be 60. But check this out. So, you know what I mean? If I know what 60 is, close to 0.9, I know what 90 is, it's 1, and 70, where does that fall? So you can do linear approximation, 60, 70, 80. This falls at a third. You know what I mean? So maybe I just increase this by a third. You know what I mean? Maybe it's 0.9. 94, 0.93, 0.933, you know what I mean? So that's going to be kind of the second method. But on some of these, I think going back and actually just, you know, what's sine of 70? It's 0.94. I think I knew that. 0.94. You know, and then you can get, you know, headachy and just start to memorize all of them. Sine of 72 is probably 0.95. Sine of 72, I remember kind of memorizing. It was 0.951. But, you know what I mean? I'm interested in memorizing, you know, like, hey, 50, 55, 60, 65, 70, 75, 80, and then 85. But that's a lot. That is a lot of 3-digit numbers to memorize. And you at least need to memorize them to 2 digits, because after you pass 70, I mean, it's really, this is 0.94. I think 75 is 0.966. And maybe you can remember that because 60 is 0.866. So then you have something going on there. You know what I mean? So we got sine 75, 0.966. So, you know, that might be the best one to remember. So let's say I did know that 60 is 0.866, and I knew that 75, 15 more, was 0.966. Well, then I can still use like linear approximation. 70 fits right there, 65 fits right here. And so we're about 2/3, you know what I mean? So still, I don't know how you're going to do that. We're 1 point off, so we need to be 0.6 more. So 0.8, 8 plus 6, I don't even know how to do that, but that's going to be 1.4. So we're going to be 9.46. You know what I mean? So 9.46, would that be a good approximation for what were we saying? 70? Well, yeah, it's decent. It's 0.94. You know what I mean? So it's not a linear scale. Yep. Because as you approach, yeah, that's interesting. So I don't know what you do. Yeah, so I think every time you should, you know what I mean, kind of do a linear approximation. Like, what's your best guess for sine of 70? You know what I mean? But here's another, we're going to slow down on this, because here's another cool thing that you can do. If I know this is 20, well, hell yeah, I know this side fairly accurate, because I could, and this is probably the only round we're going, even though I could do, you know, so if this is the only round we're going, we might as well get as crispy as possible. So 0.8 is what's 80%? What's 2 times 8 is 16. So that's going to be 160. But we know this is 0.866. We got 20 points between. We need 2/3 of them. That's going to be, ooh, that's tough, because 6.6 and then 12, 13.3. I don't even know. I can't even add those two up. I know it's going to be 12. 6 and 6 makes another 12. It's probably 13 though. So we got 13.3 repeat. Like I can't see that though. 20 times 2/3. That's a difficult one for me. But anyway, so we have, you know what I mean? We would be 13 points from 160. So we got 173 newtons. That's going to be way more accurate. Okay, so let's go to this one, because we know that sine of 30, if this is 30, hell yeah, this is just half, you know what I mean? So we're going to use that ratio, and you can use this idea that the ratio, like this is the ratio, 1/2. When I put half right here, this is the ratio of this side to the hypotenuse. And so you can actually, we're gonna use that. So I'm going to say 0.5 is the ratio, and it's associated with 30 degrees. I like to, this is factor label. You're saying, hey, this is equivalent to this. So it's the same thing as saying 0.5 ratio is equal to 30 degrees. Now what we're talking about when we say equal, and maybe you can't do this, but no, I think you can, because you're just saying synonymous with. It's, is it similar? I mean, it's the same thing. Yeah. It's a little bit different than factor label, because these two things are two different terms, but we still use them as a factor label. So how do we do it? We say, hey, I know what, so I don't know what 20 is. So I have 20 degrees. It would be cool if I could just, you know, cancel the degrees and get a cool ratio. So 30 degrees is this 0.5 ratio. The ratio is op over hypotenuse. You know what I mean? We know it's the sine component. It's this, you know, that. But check it out. So we can cancel the units. So we got 2/3 now. So now we got 2/3 of 1/2. Hell yeah. Make the denominators, make this 4/6, make this 3/6. And hell yeah. So we got 12/6. Yeah, I didn't see that one coming. What? No, we got 12/36. That's why I didn't see that coming. And 12 times 3 is 36, so we got 1/3. Oh, yeah, holy. Just cancel the 2's. Holy Toledo. So anyway, so yeah, so what does that mean? That means that our ratio is 1/3. That means that whatever this is going to be 1/3 of that. And I think we did that. I thought we did that in this initial one. You know what I mean? Yeah, we did. Instead of just saying, hey, this is 15, and we're going to say it's 125, we already jumped to this 166 value. So let's see if I can do that again. 1/3 of 500. I hate this. Like, what? How do you make this simpler? I know that you can try to get this denominator into something. Oh man, yeah, I don't see it at all. I don't see how you get. So how do we do it? I know that 300 divided by 3. So this is the same thing as 300 divided by 3, 100 divided by 3 plus 100 divided by 3. I guess I'm just taking 500 and then just having it in 3 different parts. So I know this is 100, this is 33.3, and this is 33.3. So cool. I don't know any other way. I'll think about that tonight. Probably not. But hell yeah. So now we have this component's going to be 166. I'm just going to say 167 newtons. This one was going to be 173 newtons. And this one's 100% right on at 100 newtons. And what did we say this one was going to be? You know what I mean? Did we decide on something? Because yeah, it's interesting. Like if I was just to do, I know 60 is 0.86. That's close to 9. But so 65 must be really close to 0.9. Let's see. Sine of 65. Sine of 65. Yeah. So I didn't know that. Yeah. So if sine of 60 is 0.86. Sine of 69 is 0.9. I could say sine of 70 is approximately 0.95. And then after that is just like, you know, it doesn't really matter. Sine 75, no, it slows down. So, yeah, that's where it's harder to do sine 75, 80, and 85. Just because you sine 80, what's that? Yeah, I don't know. You're 98.5. You know what I mean? Sounds like a radio station. So we got sine 75. Like, how are you going to memorize that? I just don't know. But I mean, I think I can memorize sine 65 at 0.9, and for sure sine 70. I do know that it's 0.94. That's still a hard one for me. 75. What did we think that was? That's, oh yeah, 0.966. So this little window, that should be enough. I mean, because literally, if this says 80 degrees, I'm not going to bother. Look at this. That's a 1.5 difference. Like this kind of came up on that JEE rotating disc problem. The angle was so small. The angle was 11 degrees. And let's see what that is. Because this is 30. This is 15. And we're talking 20, and it gets 20 is ridiculous. 0.94. Yeah, when it was 11 degrees, it was a 0.9. It was a 0.98. So inverse sine of 0.98. Yeah, it was, and then 90 minus that. Yeah, it was 11 degrees. You know what I mean? I'll definitely remember that one. 98% was a JEE problem that, like, people were trying to figure out the little tiny component. You know, it was potatoes compared to the bigger component. Alright, hell yeah. So I think I'm having fun, and I really don't care. Like, you know, I think, yeah, like a lot of people in my videos, they're just like, oh yeah, I learned something just a little bit every, yeah, because that's what I'm going to. I'm going over stuff that just people aren't going to go over. Yeah, but it's so useful for like the foundation of doing problems quickly, guessing, you know, approximating, not having to rely on your calculator, but not going into like a huge Taylor series, you know what I mean? Or just use the first value of the Taylor. That would be the next kind of step, is just like, but not really, because even just like the first two terms in the Taylor series, I don't know, you're still like a 4% error, and just having an intuition of what it is probably better. Okay. All right, so let's light this up. Like what are our so we're gonna be in the x direction. We have 167. I gotta do this. 167 and 173. Hell yeah! I got a 10. I got a 14. 340 in the x direction. I'm just gonna do that. And then in the y direction, we got negative. And what do we have? What was this? That was. Oh yeah, we haven't done that one. So 94. Yeah, I don't know. Like, I'm not gonna do that. That's the reason I'm not. You know, I'm gonna do 100%. That's 500. And sure, I'll do 90%. That's 9 times 5. That's 450. Cool. And then I'll halfway it. 475. I'm not gonna nitpick a 0.01. How I could do that is 475 is going to be high. That represents 95%. So I got to take 1% is 5. So I got to drop this by 5. So that is one way to approximate. Like if you are going to go for gold and try to just get a little bit, you know, hell yeah. So that's how you do it. If I found 95, we found 95 by doing 190 and then finding the halfway. I didn't even do it. No, I did it right. Yeah, 450, 500. 475 is 95%. But what's 94%? Well, we know that 1% of this is 5. So let's just drop it by 5. So we got 470. So hell yeah. So we got 470 newtons. And then this. So final answer, 570 newtons negative in the y direction, and 340 in the x. And it says determine the magnitude. Okay, hell yeah. So still, half of this is only 250 plus 30. So it's 280. So hell yeah. So this is, and then, if 280 is a half, then a quarter is going to be 140. And then so 140 plus 280 is going to be 420. So this isn't 75. Nowhere near 75. If it was 75, we'd be 25%. So we're closer to 10. And, I should figure out what 2/3 is. So on my little graph, like if I want to get a little bit better approximated, and let's just do it right now. So if I have 10 squared plus 2 divided by 3 times 10 squared, so that's 6.6, and then the square root of that, we do get 12, and 10, and then 12 divided by 10 is 20%. What was that? So we have 2/3 times 10. Like what's the percent? What's the ratio of that? Divided by 10. Yeah, that's 0.6. And so we would be at 20%. Okay, I did not know that. So I'm going to add that to my wheelhouse. If this value is 2/3, it's 20%. So if it's 75%. We multiply by we increase by 25%. If it's 2/3, we increase by 20%. If this term's half, we do 10%. But I think I do enjoy kind of memorizing this stuff, just because it allows you to see the non-linearity. If things were linear, you would just be like, there'd be no reason to have an intuition for that. But because it's non-linear, you know what I mean? It's this is a square root, because we're taking one thing squared plus another thing squared, square rooting that. Yeah, so it's just kind of cool to see. Hey, I have a triangle, and then the other thing that I haven't done with these problems is like the first thing. So let me go over it. You need to do this visually, and you don't even need like a big graph. You just go, I'm just going to go in this direction that I think this direction is, and I'm going to go 1, 2. Cool. And then I'm going to go in this direction, the direction I think it is. Just make sure your hash marks are the same. 1, 2, 3, 4, 5. Just kind of get a feel for it. But I'm going to add the vectors tip to tail, so we're going to go 2, and then I'm going to go kind of parallel to this direction. And then I'm going to go 5 again. 1, 2. I guess I didn't need to do it. 1, 2, 3, 4, 5. I didn't need to do this the first time, but hell yeah. So this is my vector. And so I already kind of know, like, hell yeah, do this. And then for sure, we're about 30. So we're about 60 degrees a negative angle of this resultant is negative 60 from the x-axis. And check this out. So as long as you did your hash marks evenly, you come in here and same thing, just kind of, forget about life and do your hash marks, and you'll probably be pretty accurate. So we got 1, 2, 3, 4, 5, 6, 6.5, 6.6, So hell yeah. So we got 6.6. Well, it was 500, so we got 660 newtons. So graphically is just, like, it's almost tip-top. Like, you can't even beat graphically, but most of this video is just like, how do you take sines and cosines and guesstimate them? That is the most important. So let's see. So what do we have? Our first guess was 660 because we did that 10% of the, we could have just said it was 600, right? And then we used 15 degrees instead of 20. We used this to be the full length. Cool, just doing a little recap. But we did do the spicier, more accurate Pythagorean's theorem. We saw that this was half, and then we took this number and increased it by 10%. On an initial guess, if this is half, I could also say just who cares, you know what I mean? If this is equal, if this was also 600, well, I can't say who cares no more. I actually go the other direction and say it's 1.5. You know, 6 times 1.5, that's 800. No, it's not. That's 900. Sorry about that. But that's what it would be. You know what I mean? But it's just drastically. The second this like drops from 600 to 450, that's going to be 75%. Hey, you only get 25% of this. Don't know what that is. 10%, 60. That's going to be 120 plus 30 and 150. So this would go from 600 to 750. And you can see the drastic reduction. You know, it's 25% reduction when this you know, my guess is a 25% reduction. But yeah, anyway, and in 1.5, that's not horrible for a right triangle with two sides of the same, but it's square root 2. It's 1.4. So you could say it's a 40% increase from the biggest magnitude, and they're both the same. All right, hell yeah. So, yeah, it's just weird how, like, sometimes I feel like, I don't know, just repeating and going over it, it's like that's the groove of my videos, but other times I'm just like, oh, this is torture even for me. Anyway, so we're going to go over that final answer. This, we got that. So we got 660 as the magnitude. That's all they were after for this. And this one, we got a magnitude. What did we do? Did we even do that? So we have our x component, our y component. We saw that there was about 2/3. Oh, we talked the hell about that. So yeah, if it's 3/4, it's 25%. If it's 1/2, it's 10%. If it's 2/3, it's going to be 20%. So cool, we're going to take 20% of this, don't know it, but 57 is 10%, 114. So we're gonna add 114. I can do that in my head. That's going to be 6. Can't do it. It's going to be, yeah, that sucks because 70 plus 41, 70 plus 30, I'm going to have 11 extra. So this goes to 6, 7, so it's going to be 7, 11. You know what I mean? Sweet. So that's going to be our magnitude, 7, 11. And I'm so bad at that. Yeah, 5 plus 1 is 6, but then this adds up to more than 100. So for sure I'm going to have 711. That's the total magnitude, so that's what we should find. 711, final answer. This is the most accurate. And let me, I got the answer in the back of the book printed out, so let me go get it. Alright, hell yeah. So I must have a mistake somewhere, but this really shows that just from the graphical perspective, like where's our little graph? Doing a graph, we thought it was 660, and it's 666, and hell yeah. So this, just doing graphically, was way more accurate. And I guess we got caught in the weeds here. Like we must have done something wrong. So let's do this. Let's do the square root of, let's see what we did. 570 squared plus 340 squared, and square root that. Yeah, we did. That's 660. What did I do wrong? I said that if this was 2/3, we would have an increase of this value by 20%. 10% is 57. So 20% is going to be 114. And I'm going to add 114. Oh, 114. I don't know where I got 100. See, I don't know where that. Okay, so I just did poor arithmetic. But this is cool because we got a guess and check that we've done 3 times. And for the life of me, I can't see that stuff. I can't see that, whoa, we got 711, and what our initial guess was 660. You know what I mean? So that's why I enjoy doing this stuff, because I should be putting asterisks on the page when stuff like that happens. Not that I have to pay too much attention to it, but it should be an indication, because the human mind will just say, oh, it'll just try to weave that into reality. The second you kind of get a funky number, like your brain does not want to register that there's any sort of error just because it doesn't know where to look. But then the second you actually say, nah, that is wrong, you can kind of backtrack and find your errors pretty simply. Okay, so what is this? You know what I mean? So we got 4, 7, 8, and then 6. So this got 684, which was still high. So that's kind of a bummer. So but if we did it so it's not 20%, you know what I mean? So 570 times 2 divided by 3 is 380, and we don't even have that. We got 570. We got 340 divided by 570. We got 60%. So yeah, I should have. So yeah, this is where, yeah, even estimating high can really change your magnitude. Because if I just went back and took this 570 and said, hey, we're just going to do a 10%. This looks about half, and it's going to be a little bit more. But yeah, so we should get an undershot. So if I take 570 plus 57, I'm going to get 100. I'm going to get 627. And yeah, and if I yeah, so there you go, 627. Yep. But I think what this shows is, like, sometimes when you do like a guesstimation, you'll guesstimate high on one term and low on another, and sometimes magically you'll get really close to the exact answer. So that's kind of, I think that's kind of the gist for this problem. Where if we go back and be like, well, how did we get such a close answer? It's like, well, we overestimated this. We overestimated this. We underestimated this. And this was right on. So this was an underestimate. And these were like, I'm sorry, but these were probably slight overestimates. You know what I mean? So let's actually see the difference. If I do the square root of 600 squared, well, I guess I don't know what I'm comparing. But yeah, this was 660. Had I used this higher number, I guess that's what I'm saying. If I used 200 plus 166, squared that, plus 600 squared square root, yes, then I get 702. If I use this, like this term, which was fairly accurate, but these were high. Both of these terms were high. We're saying the cosine component was the hypotenuse. So this should give us a high, and it would give us 702. So just in our guesstimation, I mean, just because this was low, so that's kind of what happens when you do simple guesses. Some terms can be high, some terms can be low. I don't think I would shoot for, trying to make that mesh, because sometimes you're just trying to get some answer in the ballpark. You know what I mean? If the answer is 666, I would be happy with anything from 400 to 800. You know what I mean? That's going to be, like, what would be the most error on that? So we would have 666 minus 400 divided by 666 times 100%. We would have 40% error, but still, you're still within an order of magnitude of 10. And how you do an order of magnitude calculation, you multiply by the square root of 10, and you divide by the square root of 10. So this is dividing by 3, so this is your low term, 666 divided by the square root 10, and then 666 times the square root 10. So had I just guessed anywhere from 210 to 2,000, is that, yeah, 2,106. See, this is a magnitude of 10, where 666 happens to be just right in the middle. Because if I go 666 minus 210, and then 2106 minus, no, that's I don't know where I got that. 1440. Yeah, never mind. I can't spout that. Like, yeah, for an order of magnitude, that is definitely not in the middle. So I kind of forget what was up there. But anyway, so yeah, you just kind of want to get an order of magnitude of 10 sometimes, and that can be a good enough estimate to catch errors even. But I don't know. These vector problems, you already it might be hard to catch any error that's within 5 or 10%. So hopefully your guess is close to 5 or 10%. Alright, hell yeah. So that was guessing on this one. I think we learned some stuff, but anyway, not that great of a video. We'll try to do better. I really like this idea of guessing and just kind of doing a rough guess and then improving upon your guess. But in both videos, I've made mistakes on that last improvement, and I wasn't able to catch them. Alright, so thanks for joining me, and that's the video. Alright, hell yeah. So we're going to go over my guesstimation techniques, and we can just get into it. So it says determine the magnitude. So we're going to get some components of a resultant force. And I think for guesstimation, the first thing that you want to do is actually just draw a picture. Like, these aren't to scale. This should be 8, so we're going to go just real simple. 1, 2, 3, 4, 5, 6, 7, 8. And then we're going to add these. So we're going to add 8, and then we're going to go at a 30-degree angle, you know what I mean? So just kind of pick what you think 30 degrees is, I don't know, like that. And we're going to go 6. So I'm going to just go 1, 2, 3, 4, 5, 6. So this is the direction. And so what does this ask us? Determine the resultant, so the magnitude, and its direction, measured counterclockwise from the x-axis. Well, how I do that graphically, just for a guesstimate, come to your axis, do the 90, sweep out a quarter circle, and then instantly put 3 hashes, because it's really easy to hash this up into 30 degrees. And then come in and do your 45s. You know what I mean? This would be 15, this would be 75. But hell yeah, we got 45, and then you can come in again and then hash like 3 times. Or just hash 2 little hashes in between, and that's going to kind of split the difference. But this is about smack dab between 45 and 60. So, you know what I mean? That would be 65 plus 2.5. So we got 67.5, you know what I mean? Kind of splitting hairs if we're trying to get that accurate. But hell yeah, we'll just call it 68 degrees for our initial guess. Alright, so now what we're going to do is use the components. So this, I'm gonna just leave this up for a few seconds. This is Pythagorean's theorem for a right triangle. Side A, side B, hypotenuse. And if both sides are the same, then the hypotenuse is going to be 140% of the biggest side. And if this is the biggest side and the other side is like 3/4, we can multiply by 25. If it's half, if this is 10 and that's 5, or like 7 and 3.5, doesn't matter, the hypotenuse is 10% greater, or 110% times this bigger number. So that's kind of what we're going to be using. Also for the approximations, we're going to say small angle all the way up to 60 degrees. So 1 radian, and the other way to think of that is if I have an angle of 60, it's really close to 1 radian. So if I have 1 radian here, and this, and so what do we have for, you know what I mean, let's say this is 600 newtons. That's my radius, and what we say is that this component, the vertical component, is equal to the hypotenuse, is equal to, if this is 1 radian, it's 1 radius. The radius is 600 newtons. So hell yeah, we're going to use that. That is a more technical way to do, you know, just extrapolate. If we're saying that 0.5 is equivalent to 30, then 1 is equivalent to 60. That's also what we're saying. And so, sweet, let's do it. So we are literally going to say that this distance, this component, is 600. That's our initial guess. It's really simple. This can come from knowing that sine of 30 is 0.5, but it could also come from the fact that, hey, I know that 60 degrees is approximately 1 radian. And if this is my radius, this vertical component is equal to the radius. So if I know that half a radian is approximately 30 degrees, you know what I mean, then hell yeah, I can just say this component's half the radius. So that's 2 ways to get there. But I don't know anyone that wouldn't know that sine 30 is 0.5. It's like the only one that actually has a, what do you call it? Just a non-square root. Well, what's a number that goes on forever? You know what I mean? Square root 2 goes on forever. So, but 1/2, hell yeah, that's a number. So anyway, that's the only one that's actually, you know what I mean, quote unquote number. So hell yeah, so this is going to be 300 newtons. All right, so now we can do our components. 8, 3, that's going to be 1100 newtons. in the y direction, and then what do we have? We got 600 newtons in the 600 newtons in the x direction. So this is a triangle that's going to be 1,000, 100, and 600 up. So it might look like that. We're just trying to find the hypotenuse. So this, like you could also do this graphically. I could go 11 little dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then go 6 dots up. 1, 2, 3, 4, 5, 6. And then draw this, and then just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, maybe 14, but 13.8. That's actually, I'm going to put that in my wheelhouse, because that's literally trying to find this angle. Like, how did we do that? Well, we did this graphically. But right here, we're doing this graphically. So we're saying that this is going to be... Oh, and we did it wrong anyway. So this is positive 800. This is negative 300. So we're going to have 800 minus 300. And that's going to be a positive 500. So my bad. So this is going to be positive 500. And so we're going to have 6 over. 1, 2, 3, 4, 5, 6, 5 up, 1, 2, 3, 4, 5. Drawing this as small as possible, you're actually going to be more accurate. And so here is our direction. And just from the guesstimation perspective, like, why is this angle different? Well, what did we hella overestimate? We hella overestimated this distance. If this distance was smaller, well, hell yeah, we might be right there. And then we might be more similar. So anyway, so right now I can say that, hey, what do you think this angle is? Do my 180 or 90 degree sweep, half circle. I don't know, I'm going to say it's really close to 30 degrees. So this guess was... I think this guess was just absolutely wrong anyway. Because what did we say? We said this was... No, we were halfway between 45 and 60. My bad. So 45 plus 50. Yeah, we would be 52.5. Yeah, see, my arithmetic is pretty bad. So our initial guess was 53. This is 30 degrees. So we're a little bit... this was a poor guess, but yeah, that's probably why I wouldn't start with a graphical method. I would. I mean, you definitely want to do a graphical method right off the bat. But when it comes to guessing, the graphical method is going to be like literally the best ever. You know what I mean? Because, and did I do the graphical method? No, I didn't. No, I didn't. Yeah, I went 8 up. So we went 1, 2, 3, 4, 5, 6, 7, 8. And then we went at this 30-degree angle. I'm just going to try to get... and then we went 1, 2, 3, 4, 5, 6. And then so to go from here to there, this is our vector. Alright, so yeah, and this looks like a 45, you know what I mean? I guess halfway. I should have done that for this one because it's so close to halfway. Yeah, I'm gonna say this is actually 43 degrees. And our first guess was 30, so now we're going to improve our guess. We're gonna know that cosine 30 is 0.866. I'm just gonna call it 0.9, and so we're gonna have 90% of 600. I don't know what that is, but 9 times 6 is 54. So this is going to be 540 newtons. We're going to have... and the other aspect for the magnitude. If this is 600 and the other component's close, you know what I mean? If this is 600 and this is 600, my initial guess can be 1.5. If that's the case. I know it's 1.4 if these are both the same. Now, if this is 3/4, though, because what's this half? That's 300, and then what's a quarter? It's going to be 150. So this is actually closer to 3/4 than it is to being 600. You know what I mean? And so at 3/4, I know from my little chart that we're only going to get 25%. Yeah, we're going to get 25%. So I'm going to have 600. and I'm going to get an increase because we basically have this is 6 and this is 5, so we have 6 and 5, or 600 and 500, and I want to know this length. And I could just do this 1, 2, 3, 4, 5, 6, but let's guess first. So we're going to do 25%. Don't know it. 10% 60. 120 is 20% plus another 30. So we get 150. So I'm going to say 750. I'm going to say this is 750. And would that be the case? 1, 2, 3, 4, 5, 6, 7. I don't know, 730. So there you go. Somewhere between 750 and 730. The graphical method is always going to be probably the best. You know what I mean? So, this gave us an answer of 750, and now we're going to try to improve upon that guess. We know that, yeah, but that's about it. I would say that's good enough. You know what I mean? I can say that, yeah, I think that's splitting hairs to even, like, I got into the habit of, like, oh, let's find 0.8, and that's going to be 8 times 6, which is 48. This is 54, but then this term is going to be 2/3. So if it is, like, you know, it's actually not that hard. You know, it's going to be 520. So a better estimate for this is not 540, it's 520. And so we're going to have 520 in this direction. This won't change. This is still going to be 500 up. So we're going to have 500 up and then 520 this direction. 500 up, 520. And where did we guess that this direction? Yeah, our initial guess was 600, and we got a magnitude of 750. Pretty poor. And so our best guess is that this is 500, and this is 520. So that's going to be our best guess. And guess what? These basically are the same. 500 is the biggest number, or 520 is the biggest number, and we're going to take 40% of that. These numbers aren't the same, so I'm just going to take 40% of this number. And I bet you that's actually the smarter way to go. If there is a small difference in these, taking 40% of the smaller number. And so let's actually see that with the calculator. We got 520 squared, square root 520 squared plus 500 squared. Is that going to be 500 times 1.4? No, that's going to be undershot. 520, so 520 times 1.4. Had we had done it that way, we would have got 728. So yeah, still, if these are fairly close, yeah, you still want to take 1.4 or 40% of 520. Don't know it, but I do know that 52 is 10%, 104 is 20%, so 208. So I'm going to add 208 to 520, and we're going to get 728. So that's how I get that, and that would be my best guess. I would say the magnitude is 720, but now we want to know what the angle is. But I think the only way that I'm going to do angle is just by graph paper or graphically. So if I want to get a better idea what the angle is, I'm going to go 1, 2, 3, 4, 5. We'll double this, so we're going to go 1, 2, 3, 4, 5. Might as well say that each of these is 1, and so this is 5. This is 6, 550, 525. So there's 520, and then we have 500 up. So I'm going to go 1, 2, 3, 4, 5. So booyah. So this is going to be our point, and you can see that our angle is very close to 45 degrees. No duh. If this is 520 though, and this is 500, that's what we have. Then the angle is going to be a little bit less than 45. So I'm just going to guess it's 43 degrees, and then just get on, because I just wouldn't be able to draw this in and then register just visually what it is without a protractor. But hell yeah. Okay, so we're going to look at this answer in the back of the book and just do it the slow way. So, yeah. So we got F23 And the answer is 720. So yeah, we were high at 728, but we did a pretty good job of getting there. And like, where did we start? So we thought our initial guess was 750. And let's just do one more. It's always good to go back to a problem and be like, well, couldn't I have gotten there just real fast? And definitely the graphical method will get you there. If you so we're gonna go 8. We're gonna go 1, 2, 3, 4, 5, 6, 7, 8. Those hashes aren't very good. You know, they're not very evenly spaced. But we're gonna go 1, 1, 2, 3, 4, 5, 6, and then we're gonna say this is our vector, and we're gonna go 1, 2, 3, 4, 5, 6, 7, and I would have guessed over 750. Yeah, so still, from a very simplistic graphical method, I would do 750. It's actually hard to know what a 30-degree angle is. You know what I mean? That is difficult. So let's try that one more time. So we're gonna go 1. This is 5. This is 8. How would I do a 30-degree angle? I know that. Yeah, I would almost, you know what I mean, if you can measure anything, then you know what I mean, if you have something that's 10 units long, I'm going to drop 5. So I'm going to go 1, 2, 3, 4, 5. So it's just where this hits that axis. You know, that's probably the simplest way is to get something of length, measure halfway, and then you know, I mean, from your point, come down here. You don't even have to be accurate. Is that right? I feel like I didn't do that. No, yeah. Wait, how did that not work out? So if this is my length and halfway. Oh yeah, sorry. Halfway is right about there. So yeah, so we were close. This point just got off a little bit. So sweet. So we have that 60 degrees. We have that 30 degrees. And so we're going to go up 8 to this. So this is 8 units. And then we're going to go 6 in this direction. So, and if you do have graph paper, I mean, it's fairly simple where you just don't have to still use these. So we got 1. All right, sorry about that. We ran out of juice. And all right, sweet. So what are we doing? We're going up 8, and then we did a 30-degree angle by, for sure, just kind of measuring the length, finding halfway, yeah, measuring that out. But yeah, we can use these little squares, and we're going to go 6. So 1, 2, 3, 4, 5, 6. And now, here's our vector. Here's tail to tip. This is our resultant right here. And we can still use these squares to figure out the length. So I did that. And then we get 1, 2, 3, 4, 5, 6, 7. And even right here, I can see that it's not halfway. It's about, you know, I guess 725. So that was my guess. And it just shows you that, man, for these vector problems, doing them graphically, even if it's just a quick sketch where you're trying to make the units, you know, kind of the same, and then going from here to there, and then counting those up, it's pretty darn accurate. It's going to be actually, like, maybe way more accurate than just a rough guess. But still, I'm going to end this video with just going back to being like, what was the roughest guess? It was 800 minus 500. So that was going to be, no, 800 minus 300. So that's going to be 500 in the up direction. And then sideways, we're going to have 600. So, booyah. So 5 and 6. And I'm going to say, hey, these are fairly close. We were going to take our 1.5, you know what I mean? Or I could either do 1.5 or I could do 1.25. 1.25 would probably be more accurate. 1.5 is going to be easier. My magnitude is going to be 900. You know what I mean? If I did halfway between, that would probably make more sense. And my estimate would be 570. So even what we're talking about is 900 ain't the worst. You know what I mean? It's a lot of air. like what did we say the actual answer was? 420. So if we did choose 900, we're going to have 900 minus 720 divided by 720 times 100. Like we have a 25% error. But when it comes to like order of magnitude, I mean, we're just trying to get a kind of a ballpark. One, you actually get the magnitude. And if you do this, you can get the direction. We're going to be 600 this way and then 500 up. So it's like literally just that fast I can see that this angle is going to be less than 45 because this would have to be 600. And even just doing that, I could go 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5. Draw this arrow, put my axis, see where, it's not very good. But anyway, I think 45 is close enough. I mean, if we're already way, roughing this out, yeah, shoot, we got a 45-degree angle. It's at least in that quadrant, and it's got a magnitude that's somewhere between 600 and 900. So that was kind of the information that we have. And yeah, even just doing that, that's almost a better way. If I know that my component is potentially overestimating at 600, and we have 600 and 500, then, definitely 900 is my top end, and maybe 600 though is a lower value. So I know my answer, my magnitude is going to be between 6 and 900, and then my angle's 45, close enough. And then we could then look back to be like, well, this was overestimated, which made this component longer. If this is underestimated, then my angle gets steeper, and so maybe we actually do get an angle of like 46. So, did we even, I don't even think we looked at the angle for this, and then we'll call it a video. So sweet. So we have 500, I don't know why I just look at a number and say it wrong. So we have 721 newtons, that was the answer, that was the magnitude. And our angle measured from the x-axis, they're going to call that phi, and they said it's 43.9. Now does that jive? That it's shallower. That means my x component is going to be more. And isn't that what we find? The y component was 500. This component was like 520 or something like that. Alright, sweet. So there you go. So, we haven't typed a sine or a cosine into our calculator for this one, I don't think. And it was a pretty good estimate for this problem. Alright, so hell yeah. Thanks for joining me, and that's the video. Alright, hell yeah. There is nothing worse than a problem where you have to resolve a force into two directions, and guess what? These directions aren't orthogonal. You know what I mean? If you do have orthogonal directions, it's just the brilliance of adding vectors. That if I literally, vectors are like, hey, if whether you're pulling something that way, you're walking that way, the one thing that you're not doing is walking that direction. But in this case, and you know what I mean, you have two directions. These are the directions u and v, but they still are, they're, so might as well simplify this problem and say, hey, resolve 30 into a vector that's going to be just in this direction and this direction. You know what I mean? And so we would call this v prime and u prime. This angle is going to be the same. And then what? You know what I mean? Once you just have the dot product, kind of the shadow component, like, hey, this direction only sees this component measured by, if this is representative, this length of this 30-pound force, hell yeah, this is going to be like 29.9. You know what I mean? Whatever. And so would this be. Cool. So if both these are 29.9, like, do adding these up give you anything useful? No. Does squaring these, 29.9 squared plus 29.9 squared, is that useful for anything? Hell no. You know what I mean? So, yep. You know what I mean? So it's just kind of an interesting problem where you're just like, hey, I want to know the component of this force in that direction. But hell yeah, these are the first chapter problems. We're actually just taking a vector in this direction and saying it's equal to two other vectors kind of in a similar direction. I think it gets nonsensical when the whole aspect of statics is like, hey, like this mass ain't moving. Like it would make more sense to be like, hey, let's make a rope in this direction, you know, kind of like the opposite of you. And so we have a rope this way and someone pulling on this rope, and then we have a rope this way. You know what I mean? And then you have some sort of chunked mass right here that's heavy, and you have a 300-pound force. And maybe this is just an overhead view, you know what I mean? And this is, you know, a floor, and so, you know, gravity isn't involved. You're just tugging, and actually there is no mass. It's just like a, you know, we just have three ropes connected. So that's one way to make this problem kind of simpler. And this gets into like, you know, hey, this component's going to be this way. You're going to tug a tension that way, and it's going to support this 30. So so hell yeah, that is what this problem is represented. So your magnitude over here that you're pulling, you know, is a little bit indicative. Like these are fairly perpendicular, so we can't say they're not perpendicular. I mean, if they were perpendicular, then you know, I mean, sure. Like this vector has a component this way and a component up. This person would have to pull that component, this person would have to pull that component. But because we've chosen to pull at, you know, that angles that might help one person and maybe hinder the other. You know what I mean? So it's kind of fascinating. Like this U could be this direction, but then the V, you know what I mean, could be at like or it'd be the equivalent of, let's say, you know, see how we have this V right here? Well, let's say we want to hold this force back by this tension, but then you choose to put a rope this way and someone on it, and they're pulling this direction. Well, if they're pulling that direction, that doesn't seem useful, does it? You know what I mean? You're just like, oh, this person is like, damn, this sucks. And so, yeah. And then with some of these problems, if you do choose to have something that's a rope, then and I choose this to be a rope, then I get something nonsensical as well. Because if this is a rope and I'm pulling at this angle, well, it doesn't matter if this is a rope or a steel rod. This person can only push on the steel rod or pull on the rod connected to this rope at 30. But then if I do have this also being a rope or a steel rod, we're going to have to make this a steel rod. And this person, to maintain like the equilibrium, is going to have to push that direction. So, so hell yeah. So I think we found a way to kind of make sense of this problem. And I was going to print off another one, but nah, don't worry about it. If I have two ropes in tension like this, and they're just pulling a stationary tree, cool. The resultant is always going to be in between, and it's the same as just, hey, one, like if this is person 1, this is person 2, it's person 3 coming, be like, yeah, like back off, I have a beefier rope, and I'm just going to pull it myself, you know, kind of right in the middle. So this is this direction, so it's these two vectors added. You know what I mean? So a person 3 could just come in here and pull in between, and they could be anywhere in here. They could be, if this is what person 1 is pulling, well, I guess, how do we phrase this? We have to phrase it, you know, one way and then the other. So if I said person 1 was pulling this amount and person 2 was pulling this amount, we're adding the vectors. There's only one location, or there's only one direction and tension that person 3 has to pull to equal what person 1 and 2 are doing. The same thing is true if person 3 comes in here and pulls on this tree. where person 1 gets to choose. So what we're going to do is, and then as long as this is 180 degrees, person 1 could be anywhere over, like, if person 1 is in this quadrant, which we're going to say, because they're not, person 1 and 2 aren't going to be in line. If person 1 is right here or right here, cool. Person 2 can be anywhere. So let's check this out. So if here is my 30 pound vector, and person 1 chooses to be right here, and person 2 chooses to be right here. So we can use, alright, hell yeah. So we use vector addition, and vector addition is pretty cool. It says like, hey, well, we first, from our origin, like draw a line to, where person 2 is, and then draw a line to where person 1 is. So person 1 can only pull in this direction. Cool. And person 2 can only pull in this direction. But when adding vectors, I can go this way. I can go, like, if person 2 pulls this magnitude, I'm to there. And then I would go in the direction of person's 1, you know what I mean? And let's say person 1 pulled a tension right there. So this would be the resultant. It's not right there. That's where we're trying to get. And then the other way I could say that person 1 pulls this amount, and then in the direction, that's parallel, person 2 is pulling that amount. So this would be my resultant vector. But I'm saying that if person 1 is here and person 2 is here, I can always get, with two things in tension, I can always get anywhere inside this quadrant. Now, if the resultant is over here and person 3 is over here and person 1 and 2 stage them, well, like I said, two things. One, you're outside of this window, so person 1 and 2 probably need ropes. I mean, these are ropes, but they need actually something to compress against this point. So, to put a force in this direction. You know what I mean? So, let's do this one, the more complicated one. How would I person 1, but now this was the tension direction, but I could go in the opposite. If this is a steel rod, person 1 can push this direction. So I could go this way, and then person 2 is going this way. So this is the compression. If person 2 has a steel bar, they can apply a compression this way. So to get to here, I would maybe go down person 2, and then in the same angle as person 1. So cool. In this case, person 1 still has a rope. That would be chill, because they have their intention. Person 2 has a steel rod. But if these are both ropes, hell yeah. As long as they're on both sides of what person 3's rope was, then we're good to go. So we're going to go in tension this way. And then so what you can just do is just draw parallel lines, especially through the point you want to get to. So I drew that parallel line, and then come in here and draw parallel lines. So this is the two ways to get there. I can go tension in person 1, they're going to pull that magnitude, and tension in person 2, they're going to pull that magnitude. So person 2's doing all the work, person 1 hardly at all, but these two vectors together represent this 30 pounds in that direction. So hell yeah. So now let's get to our problem. And so we have 30 pounds, and then we have this U and V and U. So cool, this actually is very synonymous with the dot product, because the angle between this was really small, and it meant person 2 was doing all the work. Person 1, the angle is close to 90. It's just like, well, they're hardly doing anything. So yeah, if we did come in here at an angle, and we called this V prime, hey, V prime, the magnitude, so the component along V prime would be a vector of 0. Cool. All right, so what can we see from this problem? This is 15, this is 30, and sorry, I'm not going to print this off. I'm kind of just done for the night, and sorry I kind of scribbled it, but we can handle this. We're just going to do this one time. So what's 90 minus 45? So cool, this is 45. Well, hell yeah. So this has a smaller angle. The cosine component is going to be 0.866. It's going to be almost 90% in this direction, and it's going to be 0.7. It's only going to be 70% in this direction. So let's do that. So this person, and there's a chance that both people would have to, so if I do this, if I have a 30-pound force, and that was person 3. Person 3 removes his rope from the tree. Person 1 and 2 come in, and they're at 30-degree angles, this angle and this angle. This is in rock climbing. This is where you have 120 degrees. So to get to here, and let's say this, is 30 pounds. Well, I have to go this direction, and then, you know what I mean? So here's my parallel lines. And so here's my parallel lines. And what happens is I have to go see how this is now 30? Person 1 and person 2 have to pull 30 pounds each. So I'm going to go 30 this way, 30 this way, just to equal what one person was pulling, 30. So 2 people are now having to pull 30. If this angle gets small, it can get up to infinite. But the 120 is kind of like that secret sauce window that if you're doing a rock climbing anchor, it's not the end of the world, but you're maxing out, like whatever weight you're putting on this anchor, these are the same. Instead of like having a nice anchor where maybe it's half, or closer to half instead of just, the same amount. So that's what we have here. So that's when your angle, and then look at this, that's when your angle is 60. We don't have that. If this was an angle of 60, well, hell yeah, then this component would be 30. So that would be that. That would be 100%. Now, if this angle is, all right, hell yeah. Some of these actually are kind of visually hard for me. So yeah, if we have U here and then we have V prime, well, no, I do my parallel lines and I can go this way and then I can go parallel and go this way. So I would have to have tension in U and then I would have tension in V prime. So yeah. So even though that V prime is perpendicular, so kind of forget what the hell I just said. It probably was nonsense. Yeah, I think what I said was probably almost 100% wrong. Don't know if, the whole dot product thing. That, well, it should work out where, let's think about this. So if this is perpendicular, now the dot product of this in this direction would be 0. But that's if we have orthogonal components. We don't. We have components that are just non-orthogonal. So if I have, there are like 2 people pulling, that's going to equal the same. So I'm going to go this direction and then that direction to get there. If this was orthogonal, well, hell yeah. If this was U prime and V prime, then I'm just pulling tension in U prime. With orthogonal components, this person doesn't have to do anything. But that's why these problems are tricky, where it's just like you don't have an orthogonal coordinate system. They just said, hey, what's this force, in that direction? Or resolve this 30-pound force into 2 components, which is just like saying, it's kind of, and I guess I don't understand this. It's just like, it's the same thing as saying, hey, this is force 1, and this and then in whatever direction, I kind of don't know my directions no more, but let's say this is force 2. So what we're saying is that, hey, if these are our 2 forces, what's the resultant? And let's say we know the magnitude of this and the magnitude of that, and it just happens that the resultant is 30 pounds of tension right there. Does that make sense? Because we'll go this way and that way, and hell yeah, it is. And we can just see visually that if this is 30, and we're going this way and then parallel to that, well, if this is 30, that looks 30, and this looks about 45. So now let's search out what our parameters were. Where is our parameters? I can't even see them no more. But I think this was V right here, 15 degrees, and this was U. Cool. So let's just do it graphically and be done with this one. So we're going to go in the direction of U, but then we're going to go in this direction. So let's draw a parallel line, and hell yeah. So if this is 30, it looks like we're going 20 and 20. You know what I mean? So I think the component's going to be 20 and 20. I think it's going to be 20 in the U, and then maybe 23 in the V. So cool. But I think I went over enough of that where it's just like, yeah, I think I learned something. I definitely learned something new. Just because some of these resolving forces, it's kind of one of the trickier things. So hell yeah, we got 22 in the direction of U. Okay, so it's a little bit different. 22 in U, and then 15.5 along the V direction. All right, hell yeah. And couldn't we have done that graphically? So we're gonna be just like that and just like that. I don't know. Yeah. All right, sweet. So we did this one. This is an awful video, but thanks for joining me. And guess what? That's a video. All right, hell yeah. So we have statics, and I think these are one of the harder problems. I swear, and it makes your mind bleed because we're trying to resolve this force into two components. And it's saying like, hey, this force doesn't exist, and then like what you're going to do, I like to do this. This is person 1. We can get rid of this joint. And then this is person 2. Person 1 can either push on this or they can tug on it. So I think that's easy to see. Person 2 can also push on this and tug on this. So check it out. We can get anywhere, and if we get to this point, that's going to indicate a force due to this person pushing or pulling and this person pushing and pulling. And we do it by going along this direction, and we could go, this is going to be in tension, so we'd call that the tension direction. This is going to be in compression. So we can go anywhere along this line due to someone pulling or pushing on this member. Also, this person over here can push on this member this way or can pull on this member. So to get to this point right here, we have to either go on this push, or we can go along this pull, and then we're going to add what this person's doing. And it's a free vector, so we just go down this, and then we say, hey, what's you doing? And they're going this way. So I can go down here and then go that way. Well, is that going to get us closer to our point? No. So let's go down here, and then let's go this way. Well, is that going to get us closer to our point? No. So I think we need to go this way. So we're going to be in compression. And now let's go down, this parallel path. So we're going to go this way, and then we're going to do what 1 is doing. Ooh, hell yeah. So I'm just going to go this way all the way to there. And you know what I mean? It's kind of just doing the kind of intuitive, when you get the hang of it. Because I think this is more sensical, kind of saying, hey, there's a person pushing or pulling, and this is the direction that this is the magnitude that way, and then this person is pushing or pulling, magnitude that way. So hell yeah. So person 2 is pushing. That's the component. Person 1 is pulling tension. And this is the resultant. Sweet. So now they said this is the resultant. So let's do it. So maybe we're going to be in tension on person 2. And then we're going to, maybe we're going to be in compression on person 1. So cool. And it looks like that. And the other thing to do is just find where your resultant is and be like, okay, here's one member. We're going to draw a parallel line, and you can just keep drawing parallel lines until you reach your resultant, and then draw one through. And then right here, parallel line, keep drawing parallel lines until you reach your resultant. And then go from A, you know what I mean? And we can go this way and then parallel. That's why drawing a lot of parallel lines is helpful. But we're never going to get to there going that way. So we need to be in compression, and then we go down parallel lines. So I could go here down the parallel line. Ooh, there we go. So this is going to be the compression of person 1, and then the tension of person 2. Or we could have done it how we did it, tension of person 2, and then compression of person 1. Gets to that same location. All right, so hell yeah. So I think this is, well, should we figure out, so it says this is a 450. Resolve this force into two components acting along members AB and AC. So one way you can do this is just graphically. This literally represents 450, so I could be like 1, 2, 3, 4. Almost got there, so we're going to make 1, 2, 3, 4. That's close enough for hashes. And so just keep those hashes in mind and then just do it. So we got 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5, 6. Maybe 650. So I'm going to have 650 and 1, 2, 3, 4, 5, 550. Okay, so I'm going to have 550 in compression of member CA. So we got CA is negative 550. That's how we indicate compression. Member 2 is in tension of 650. So we're going to be member BA is positive 650. And I'm just going to look in the back of the book if that was close enough. We're just doing videos kind of on guessing and checking where, you know, figuring out the angles is the least of your worries. Figuring out what the hell we just did right there was the most of your worries. Understanding the problem, and then, yeah, so guessing a solution from a graphical perspective is great. Alright, so this is 5.25. One more page and we'll get there. And so we get 869, and that's going to be AB. So that's going to be the one in tension, right? And then FAC is going to be 636. And it just says what's the magnitudes. Components acting along, determine the magnitudes of each component. So it did not, on this one, they're just saying it's like a triangle. Like they're not worried about whether it's in tension or compression. They're just interested in the magnitude. So they got 870 and let's say 640. We got 650 and 550. And did we at least get the bigger one bigger? So we have AB is 650. Yeah, close enough, you know what I mean? And then CA is 550. So we did our hashes just a little bit under, and then we made these too big. So, cool. But, you know what I mean? If you have just a little bit of graph paper, hell yeah, you can just come in and measure this. So we're just going to measure, we're going to say this is 1, 2, 3, 4, 5, 6, 7, 8, 9. You know, let's say 9 is 450. So that means that 2 of these is going to be, isn't that right? 2 of these is going to be 50. So we got, what is that? What's 45 divided by 9? That's 5. So that's 50. So 2 of these is going to be 50. Yeah, 50, 100, 200. No. One of these is going to be 50. That's what we have. So yeah, one of them is going to be 50, and we're going to come here, and we're going to be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Almost 13. So we have 13 times 50. Don't know what that is, but 1,300. Half of that is going to be 500 and 150. That's going to be 650. So, bummer. I thought we were pretty... Maybe I don't know how to do these problems. But anyway, so, and then this component is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Closer to 17. That's going to be 1,700. Half of that's going to be 500 and 350. That's 850. Okay, so hell yeah. So we're 850 and 650. I'm just a little undershot on this one. It's probably because I'm not going. I can probably add another 50 to get down this thing. So yeah, 700 and 850, and now we're in business. So yeah, it's just kind of interesting using the guesstimation skills. This problem is problem 5. Man, you probably don't want me to look this up again. But hell yeah, we're done with the video. So yeah, we just had 870 and 636. So yeah, so we were fine at 650. I didn't realize that. Oh, yeah, weird. So BA. Yeah, no, yeah, BA was the longer one, and then that's going to be 870. We guessed 850 on our higher one. This one could be 700. We were, yeah, no, CA. Yeah, CA we said could be as high as 700, somewhere between 650 and 700, and 650 was just fine on that. But yeah, these were lower. These are nonsensical anymore. These were our first initial guess. This was the bigger one, 650. This was the shorter one. But we found that this one was closer to 650 and this one was 850. Okay, hell yeah. So take home point, more just kind of on what it means to have two components. When you add them, they have to equal that. So it's opposite of kind of like static, saying like, hey, if I have this force, like what's the components resisting that force? Because that's different. All right, sweet. All right, hell yeah. So we've been guessing on vector problems, but the crazy thing is if you just do a graphical method, like it basically is the best guess you can have. But one of the commenters just like, well, where do you begin with a guess? You know, and I think you try to get as rough as possible. You know, rough as your brain will allow you to, because your brain does not like wrong answers or like, you know, it doesn't like to call 1 2. You know, it doesn't like to round 1 up to 2 or 2 down to 1. You know what I mean? It doesn't like that. But if we're adding 1, you know, and 10, yeah, it doesn't really matter where this is 2 or 1. You know what I mean? You choose, who cares? Okay, so and one of the so for this problem, like what it's saying is like if I have two forces, this could be in tension or compression. So I can either have this a rope or a steel bar. And if I make this a steel bar, I can say I can have a person right here and I can either push on this or pull on this. Cool. I'm going to do the same thing here. I'm going to make this a big steel bar connected to this point. And we have a person out here. They can either push on this or pull on this. You know what I mean? And so if both people are pulling, it's kind of cool. Your force is going to be somewhere in this quadrant. If both people are pushing, then your force is going to be somewhere in this quadrant. Now, if one person is pushing, then you actually have to do, and the other person is pulling, you need to do like a 180. If this person can push or pull, but this person can only pull, you know what I mean? This person can push this direction, cool, and this person can pull. So I can get anywhere on this side. Cool. So if both people can push, I can get anywhere. Oh, maybe I can't get. Oh, never mind. Sorry about that. I have to draw this. If I draw this, then if both people can just push, I can only be in this window. Like I can have a force vector that way, anywhere from here to here. If both people can just pull, I have to be in between these two. So don't even look at this vector. But if both people are pulling, the resultant is maybe a vector anywhere but in between these two spaces. So I can get here by going tension, tension. You know what I mean? Because this person's in this direction and this person's in this direction. Or I could go this direction and then just parallel with this person. So that's how you do it. And you can just see that, well, if it says if this person is pulling 6 kilonewtons, and this is what we call 6. Well, just visually, you're like, well, this looks like 5, and this looks like 4. You know, we're done. We're done with the problem. So it's just kind of interesting, and I don't even know. I didn't want to do that, and just the fact of saying that and doing that is just like, well, that's kind of a bummer. It kind of spoils it. What I really wanted to go over. Hell yeah. So I think we're good. So from a guessing, this still has an X component and a Y component. Cool. And from the guessing perspective, like, hey, this is a right triangle, and both of these components have to be equal. And so we know that if both, yeah, so we get that. So it's just kind of fascinating. So One thing that we're going to do is just kind of throw a number in. So this has to be 6. That's our starting point. This can be whatever. So let's throw in, you know what I mean? Let's throw in 10. Now this angle is 105. This is 90. So this is 40. This is 45 and 45. This is 90. So 105 minus 90. That's going to be 15. And is that right? Is that what I need to print off the picture again. It doesn't seem like this is 105. It seems like they way overshot this angle. But I see an arrow there and an arrow there. And or are they? Oh, they're saying 105 from here. Cool. So we have 45. So we have 105 minus 45. That's going to be 100 minus 40, and we got 60. So this angle is 60. Now we're in business. Cool. So if this is 10, one of the guesstimation things that I was saying is that, hey, this component's 10 too. You know what I mean? If this angle is 30 degrees or less, and this is 60 degrees or more, you can just say, hey, the hypotenuse is equal to the longer side. So that's the approximation we're going to be using. Cool. So if that's the case, and then if we know this is 30, this is going to be 5. So I think we're pretty much in, because we're going to say, hey, this is down 10. Well, no, we're way off, because we have over 5 and then down 10. And so we have negative 10 plus 6. This is going to be negative 4. So it actually is going to be this direction. It's going to be 5 over and 4 down. So horrible guess. So just guess the exact opposite. Guess 2. Go the other direction. You know what I mean? So this is going to be 2, and this is going to be 2. This is going to be 1. Okay, hell yeah. So we're going to have... so what do we have? So we have 6... minus 2, so we have 4 here. So we're going to have 4 now, and then this is only 1. So we have 1 over and 4 up. Okay, so, you know what I mean? And I guess my take-home point in that comment was just like, you should be able to do this 5, if not 10 times without losing your friggin' mind. You know what I mean? So do 4. Cool. Just, small baby steps. So I'm going to say this is 4, and then this is approximated at 4. Cool. So I'm going to have 6 minus 4. This becomes 2. And then, cool, this becomes 2. All right, so we found our answer. You know what I mean? We found that if this is 6 kilonewtons, and this force along FV has to be 2. Now, let's refine our answer, because if I do 4 here, I know this isn't 4. You know what I mean? It's 80% of 4. Don't know what that is, but 0.4. is 10%, and so 4 times 8 is 32. So this is going to be 3.2. So now we're going to have 6 minus 3.2. This component right here is going to be 2.8. And this component right here is still going to be 2. So I'm going to be over 2 up 2.8. This one is still too large. I need to make this one... smaller by making this component larger, this negative component. So we're going to go to 4.5. We're going to go to 4.6 because I think I need even numbers just to do this approximation. And well, and that's the crappy thing about estimating cosine is 0.866. It's close to 0.9. Hopefully we used 0.9. I don't know if we used 0.9 or 0.8. But we're going to approximate this to 0.9. So sorry if we didn't do that. But we're going to go, yeah, so we're just going to do 4.4. Okay, hell yeah. So that's going to be 0.4. Oof. Yeah, it's going to be tricky. How about 0.45? So we're going to do 0.45, and we're going to do 90% of that. That's going to be 4.5 times 9. 4 times 9 is 36. 5 times 9 is 45. So we're going to have this, and we're going to have 5, 10, 4. So we're going to be at 4 basically 4. So sweet. So we're going to be 4 right here, and this is going to be 2.3. And for sure this is going to be 2. So we overshot it. So now we need to do 4.2. If we do 4.2 and take 90% of that, that's going to be 0.42 times 9. That's going to be 36 and then 18. So we're going to have about 3.8. So if we have 3.8 here, we're going to have 1.6 for this component, and then we're going to have 6 minus 3.8, which gives me about 2.2. So this is going to be 2.2. If this is 3.8, is that what I said? 3.8. This is, oh, bummer. No, I'm sorry. This is 4.2. This hypotenuse is 4.2. So this is 2.1, and we just said this was 2.2. So 6 minus 3.8 is 2.2. 4.2, half of it is 2.1. I do need to increase this. So I know my answer for this is going to be, or this component has to be just a little bit juicier. So hell yeah, the force at V is just a little bit bigger than 4.2. Let's look this up. I think this is my last one for the evening. I don't think any of these videos I should post, but if I get backlogged, hell yeah, you're going to watch these videos, I guess. Sweet. And what do we got? So we got F, oh, hell yeah. So 6, and what does it say? It says FV. Oh, bizarre. Oh yeah, and it says what's the component. Who cares? But we found the most important part. It said this is 4.39. Okay, so our approximation is high. Because our approximation of 0.9 is high, then 4.2 is we took a low number and multiplied it by, we made this bigger. But this is actually 0.866, so that, yeah, I didn't see that. That means that this can be a little bit bigger. Yeah, so 4.4 for this was juiced out. But that is the issue you're going to get into guessing, is maybe just one guess that's fairly close and then call it a day. Because the second you try to not break out your calculator to do use exact numbers, you're always using a number that's off. So you can get an exact answer from that off number, but it's very difficult to correct. So we tried to get very precise at 4.2, and we thought we were just in, but it was because we approximated the cosine component at 90% when it's really 86.6. So hell yeah. But you know what I mean? I'm smiling on this one because I don't think this was too trivial. And I'm just glad I explained a bunch of things in the beginning about how to visualize this problem, because these are awful. Instead of just saying, hey, I have a force here, and you're going to have to resist by maybe pulling this direction and pulling that direction, it says no. It says, hey, you're going to have either a tension member, or like a steel bar. You can either pull on it and push on it, pull on it and push on it, and that's going to indicate like and then like this is almost like a dial, like a readout that says, oh, you are pushing in this direction a force of, who cares, which it's just, I think it tripped me up doing problems like this. I hate problems like this compared to just being like, hey, I have a force in that direction. What the hell does this bolt need to do to make sure this mass doesn't move? Well, it needs to pull in the opposite direction. If it can't pull in that direction and can only pull either in this way, tension or compression, and tension and compression this way, you know what I mean? You could make a system like that, then yeah, these are going to be those magnitudes. Bummer. Alright, so we're going to be done. And but yeah, those could be those magnitudes. They're just going to be opposite in direction. So as these are doing whatever to equal that direction and magnitude, it's different than, hey, having this being pulling and then this resisting. If these are resisting that force, they're going to be opposite. If these are what's causing that force, then that's what we have. But it's just really bizarre to have three forces on a page where both these are meaning the same thing. Because if you actually have this, but I guess this happens all the time. You have a force, and then you just draw the component. Alright, hell, we gotta be done for the night, but hell yeah. So, yeah, this is so wild, because even in statics, like on a page, I might draw a force vector, but I do not think twice about putting the components. But I am cautious. Like, let's say I put a force this direction right here. I try to bold in the arrow, and if I do components, you know what I mean? I try to dash the lines, one, and then open the arrows. You know what I mean? So that is my method, where it's just like, hey, this is not three forces, you know, because I could put this component this way, and hell yeah. And then it just shows you that you don't even have to dash the lines, but just soliding, you know, this is the force, and maybe the components of this in the X and Y direction are going to be this direction and that way. So sweet. But this is not representative of three different forces at the point. But these problems where you have to take the force and resolve it into two components, yeah, that might be useful to be like, oh, this is the force on this steel chunk of whatever. And so I just want the components of it, and so I can do this, open-faced arrows. And so it's like, and you need a light switch. You're like, off, on, off, on. Both are the same things. They're equal, and it's because they both have lines of action through the same point. And I think there's terms for that. You know what I mean? But hell yeah, light switch on, off. Both are representing the same thing. So, but because I do enjoy how awful and confusing some of the easiest stuff is in textbooks. It's fascinating. Like calculus is that way with the darn limits. But hell yeah, definitely that's equivalent to statics. You know, saying, hey, here's a force. Make two components. Resolve. Even the word resolve this force into two components. Yeah, you have to have a light switch. This means that. On, off. Alright, I think we did pretty good. You know what I mean? These videos are just for me to learn how to teach at a later date. And if I say it to myself, like, you know, I can definitely tell where I'm lacking, or being like, whoa, I get it now. But it's having the courage to go through. I don't know if it's courage. You're probably just like, this is awful. So anyway, thanks for joining me, and guess what? That's a video.